Chapter 3 test is the 22nd. If you want to write that on the front of your packet, just so that you don't forget. We had left off on that worksheet that I had passed out to you guys on Friday, because again, it's very similar to your homework, which is due tomorrow. Homework is due tomorrow night. All right. So we talked about the slope, 5.125, and we said for each additional minute Dion works out, the model predicts that she climbs 5.215 more floors, or a predicted increase of 5.215 floors for each additional minute. Really, 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 really important when we are interpreting the slope and the y-intercept of a regression equation. We always want to say that it is a predicted increase or a predicted decrease, a predicted starting amount or whatever. Regression lines don't tell us about actual observed values. They always make predictions. Do you guys remember what our y-intercept was? Check the box up at the top. What was our y-intercept? Yeah, negative 3.822. So what is that representing then? What is the model predicting, that negative 3.822? What is it predicting? Started. So when we're thinking about our two variables, what's our explanatory variable? What's our response variable? What's our x? What's our y? Explanatory variable is workout time, so that's our x. What's our response variable? Number of floors that she's climbed. That's our y. When you think about a y-intercept on a graph, think about that ordered pair. The ordered pair always has a 0 in one of those spots, right? For a y-intercept, which spot, the x or the y, is always going to be a 0? For my y-intercept. What does this look like? Think about a graph. If I have a point on the y-axis here, what would that ordered pair look like? Yeah, it's going to be 0 and then some number, right? I don't necessarily know what that number is, although we found it on ours was negative 3.822. But it's going to be 0 here and then our y-intercept. So I want to interpret this 0 in context. So that's my x variable. What did we say our explanatory variable was? Number of, yeah, that's our workout time, so number of minutes. So it's saying that at 0 minutes of workout time, the model is making what kind of a prediction? Yeah. If Dion exercises for 0 minutes, the model predicts that she climbs negative 3.822 floors. That doesn't actually make sense in the context of our problem, but that is what the model is predicting. Is a line the most appropriate model for this data? What do I want to look at to determine that? Danelle, do you have that worksheet that I passed out on Friday? Because that's what this is on. How do I decide if a linear model is the most appropriate? Look up at the top of the page. There's that box with all the data, and then what's off to the right side at the top? The graph. What is that a graph of? What kind of a plot is up there, top right? The residual plot. Do you guys see any kind of a pattern in that residual plot? I don't really see a pattern to that. It just kind of looks like random scatter. If you see random scatter in that residual plot, then a linear model is the best fit. If you see a clear pattern, like it starts high, goes low, and then comes up high again, so it almost has a U shape to it, or it starts here and then it radiates outwards, like you would see a very clear pattern, and then you would say, linear model's not best. If you cannot identify a clear pattern, it just looks like scatter, then a linear model is the best choice. And then we still have interpreting S and R squared. Do you guys remember what S means? Standard deviation of the residuals. S is telling me the standard deviation of the residuals. So what's the average distance of any of these observed points away from our least squares regression line, our line of best fit? Once you're done copying part E onto your worksheet, I want you guys to look up at that box in the upper left again and tell me what our value for S was. 2.3472. So that 2.3472 is telling me that the actual number of floors that Dion climbs is approximately, typically, 2.3472 floors away from the predicted number of floors. And that prediction is being made by our least squares regression line. That's what that LSRL is, least squares regression line. Oh, you need another one? Not a problem, sir. There you are. And I have all of this posted on Canvas, so you can go back and fill in those other pieces. For the homework that's due tomorrow, you'll find that this sheet is really, really helpful to help you walk your way through some of those parts. What was the value of R squared from that box up at the top? $93.9. Or sorry, 98.9. My apologies, I misheard you. R squared is 98.9. We don't want to use the R squared adjusted. We don't pay attention to any of the adjusted pieces in that box. R squared is telling me that any of the variability that I see in the number of floors climbed, 98.9% of that can be attributed to this linear relationship with workout time. So number of floors climbed is changing because the workout time is changing, and most of the change that I see there, 98.9% of the change that I see, is due to this direct linear relationship. For this next part, you're going to need a partner and a computer between the two of you. So 2 people, 1 computer. If you're still writing, go ahead and grab your phone and snap a picture of the screen real quick, because I do want to pull up this next piece so that you guys can see where we're going from here. You can either type in the URL directly, or you can click on the link that I have on our Canvas page for today. So we're going to be in your books, we're going to be in your packets. It is on, I want to say page 15. Yeah, page 15. We are going to do a little bit of an investigation about how outliers are affecting our least squares regression line. So I've got the link right here. You can click on it or you can type it in. It's tinyurl.com/regression applet. REGRESSIONAPPLET. If you want to type it in, or you can click on the link. That's going to take you to a page that looks like this right here. And what I want you guys to do with a partner, we're going to add 10 points in here. You just click to add a point. We're going to put our points down here in this lower portion, like lower left. And I want to watch this as I do it. So I've put a couple points down here. It starts to tell me my R value, my correlation coefficient, as I get several points on here. I want 10 points, and I want to get that R value reasonably close to 0.5. So I'm going to put points down. I've got 5 points up here. I'm at 0.4. I'd call that good enough. So you want it to be reasonably close to 0.5. Get 10 points on there. If you find that you need to remove a point, you just click that point again and it'll take it away. But you want your R value reasonably close to 0.5. Yes, ma'am. Oh, lovely. Let me fix that. My apologies, guys. I thought I had unlocked it last night. All right, reload the page and it should work now. So I want you to get your points on there, and then there are 2 check boxes down here that I want you guys to check. We want to show the least squares regression line, so I'm going to check that. So there's my least squares regression line, my line of best fit for the points that I have. And then I'm going to click the checkbox just underneath that says show mean X and Y lines. Those gray lines that it just put in the background, that is not the XY axis. That is the average X and the average Y. You want to get your sketch on there. So you've got spot at the top of your page. Once you have your 10 points and you've checked it like this, you want to get a sketch on there. And then there are 4 different pieces underneath number 2 that I want you to investigate with your partner. And question number 3. So you guys are going to add a point for A, for B, for C, for D, and I want you to see what happens. The Y-intercept is going to be back here. Oh, that's a mess. So like this is my Y-axis here. This is my X-axis. This right here is the mean of Y. This line right here is the mean or the average of X. That is not my X-axis and Y-axis. I'm going to give you guys about 10 minutes. Once you get your sketch on there, you want to go through, read on number 2, A, B, C, and D. You're going to add a point to this picture. So add a point for part A, see what happens, record your results, and then take that point away by clicking on it again. Then for part B, you're going to add the point that it is describing, see what happens, record your results, click on it again to take it away. I want you to see what happens as you add the points that they are describing. You guys have 10 minutes to investigate this on your own, and then we're going to go over it together. All right. So I'm going to talk about what happens here. If I add a point to the far right, so like over here, what happens to my slope? Did my slope increase or decrease? Decreased. What about my y-intercept? Increased. It went higher. What happened to the correlation coefficient? Decreased. So my slope decreased, my y-intercept increased, my correlation coefficient decreased. What about if I add it to the far left over here? What happens to my slope? What happens to my overall slope? Increase or decrease? Decrease. What about my y-intercept? Increase. What happens to my correlation coefficient? Decreased. So slope decreases, y-intercept increases, correlation coefficient decreases. If I add a point below the least squares regression line, so down here, what happens? Does my slope change? Does the y-intercept change? Decreases. Does my correlation coefficient change? What happens to it? It decreases. So my slope remains the same. If I put it on that mean line, slope remains the same, the y-intercept decreases, and the correlation coefficient decreases. What happens if I add a point above my least squares regression line? Does my slope change? Nope. Slope remains unchanged. Does the y-intercept change? It increases. What about my correlation coefficient? Decreases. All right. So I've got my sketch here. Keep in mind, this guy right here, again, was not our y-axis. That was the mean of y, or the average of all the y parts of my ordered pairs. That's what that horizontal line was representing. The vertical line is representing the mean of x, or the average of all the x parts of the ordered pairs. Right where these two are crossing, x bar, y bar, that's the mean of all the y values, the average of all, or sorry, the mean of the x's, and then the mean of the y's. Average x, average y. Where these two lines cross each other is the center of gravity. That's the balance point for this. We saw decrease, increase, decrease. Same thing for part B. Notice if I am having an outlier on the horizontal, it tilts my line. If we add a point below, slope stayed the same, y-intercept decreased, correlation decreased. When we added a point above, slope stayed the same, y-intercept increased, correlation decreased. All this did was serve to shift my line up or down. The line slope didn't change, but it shifted up or down. What stayed consistent throughout all of these?
Correlation.
Correlation decreased. Every time we added an outlier, every time we added something that was out of the pattern, something that had a large residual, our correlation decreased. Which of these outliers, the horizontal ones or the vertical ones, made the biggest impact? Which one made the biggest impact, the most overall change? Horizontal. Our horizontal outliers made the largest change. We call our horizontal outliers high leverage points. If you think about that center of gravity, x bar, y bar, the average of x, the average of y, kind of as the fulcrum. Horizontal outliers, if you think about a teeter-totter, the further out one person is, the greater the impact of their weight. Have you guys looked at levers and fulcrums in physics at all? When you move that fulcrum, if it's balanced right in the middle, both sides have equal weight. When you move that fulcrum over, the farther away you are from that point, the more weight it's going to have, the more leverage it's going to have. Influential points. We consider something to be an influential point if when I remove it, it substantially changes the slope, the y-intercept, or the correlation. We have an influential point if that one point by itself is making a huge change to my slope, my y-intercept, or my correlation. When we're talking about two variable data, anytime I have a scatter plot, I'm working with two variable data. Outliers are anything that is outside of that pattern. So if it would fall close to or on the least squares regression line, even if it's far away from the rest of my data, I would not consider that an outlier. An outlier is going to be something that is far away from the rest of my data and not following that pattern. So if I go back and look, I'll pull this right back up. If I had a point out here, that did not fall outside of the pattern. My pattern is anything that is on or in line with this least squares regression line. Points out here drastically change my slope. Those are going to be those high leverage points. Something like this would not be considered a high leverage point, would not be considered an outlier because it is inside my pattern. Does that make sense? All right. Back side of this page, page 16. Big ideas for today. Outliers are anything outside of my pattern, things that have large residuals. It is high leverage if it is a very small or a very large x value. Things in the horizontal direction are considered high leverage points. We consider it influential if when we remove it, there are big changes to the slope, the y-intercept, or r. Outliers and the least squares regression line. Horizontal outliers are going to tilt our line. Vertical outliers are going to shift our line up or down. A good least squares regression line has a low S, low standard deviation of the residuals, and it has a high R squared, something close to 1 or 100%. For this part down here, you will be given these formulas anytime you would be expected to use them. But we can find a least squares regression line given information about what R is, what is the standard deviation of Y, what is the standard deviation of X, mean of Y and mean of X. We can use this information to come up with a least squares regression equation. When you guys are done copying this down, I do want you to try the check for understanding down at the bottom of the page. We will go over those pieces with our last couple minutes of class time. Which point is part A talking about? Which point do they want us to focus on? Where's the point that goes with the student that was assigned to practice 14 times?
14 and 8.5.
Yeah. This guy right up here. What would that do to the overall line?
Increase the slope.
Yeah, it's gonna change our slope to something like this. So it's gonna make it less negative. It's gonna increase our slope. It's gonna make our Y-intercept go down. What do you think that would do to the standard deviation of the residuals to S? Would it increase or decrease S? It's going to increase S. What about R squared? Decrease. The standard deviation of the residuals S is going to increase. R squared is going to decrease. Last bit, I want you guys to snap a picture. Sorry, let me get all of this up here. There we go. To find A and B, you take the R value, which they gave you in the paragraph down here. They gave you the standard deviation of Y and of X. They gave you X bar and Y bar. All those pieces of information put together can help you find the least squares regression line. All right. 3.2 homework is due tomorrow night. I will be getting the test review out to you guys probably midweek, Thursday or Wednesday, Thursday this week. Test is next Thursday. Let me know if you guys have any questions, especially if there's anything that you need to know as far as like wording. Absolutely want to clarify that for you.